Hello, everyone. This is Scott, your instructor and best friend and guide into sets and multi-sets. Today, we're going to be talking about associative containers, which is actually interesting. You might say, hey, Scott, didn't we just start talking about trees like a couple days ago? Well, yeah, you're right, but we got stuff to cover, so we got to keep moving. So I'm going to do a quick overview of the hierarchy, not the hierarchy, that's the wrong word, what the kind of the idea behind an associative container is and how they compare to other containers, and then we'll get into sets, which is the first associative container we're going to talk about. All right, so sequential containers, that was what we first started talking about. Those were things like, I guess I got my examples next. So right, sequential container is going to be some kind of container that holds in order data. That in order part is important. That's going to be some kind of sequence. That's going to be some kind of relation to each other. Specifically, that data is stored in reference to another thing. In a linked list, that's using pointers. In a vector, that's using an array. Right? In a DQ, it's using kind of both. The whole point, though, is that if we think about a string, strings aren't really useful if they are not ordered. If it's just a random mumbo jumbo of characters, that's not particularly helpful. Now, I put that asterisk there because it depends on what you're doing, right? There are some cases where you don't actually need to know the order for some string operations, but right, that's a minutia. All right, so examples, right? We've got array, we've got vector, we've got list, DQ, queue, stack. You guys are all champions in sequential containers. That was also last exam. We don't have to talk about that anymore. All right, we started talking, though, about hierarchical containers or containers with hierarchy. These were getting into the idea that we had some kind of meaning in the storage of the data, not just in the representation or the association of the data. Where this gets into the idea of, well, we can come up with this hierarchy of what's in a tree, but then it gets into, well, how do you iterate? I know some of you are working on that extra credit for the binary search tree. That's why it's extra credit, right? Iterating through a tree is weird, and it's not, it doesn't feel right. So that's why it's extra credit. But the whole point here being that the hierarchy is much more important than the sequence. When we're talking about a heap, we care a lot more about the nature of the heap, if the largest object is on top, as opposed to caring about the order of the elements in our heap. Right? We care about the storage of our data and how it is being stored, not necessarily how it is in relation to each other. Okay, so our examples that we've talked about in this class at depth is the binary search tree. This is the idea where we have things that are smaller than a node being on the left and things that are larger than a node being on the right. And then we have our heap. In the case of a max heap, the largest item is on the top. When we talk about a min heap, just as a side, right? A min heap is just the lowest thing or the smallest thing is on the top of the heap. In this case, we're talking about max heap. Right, so the whole point being that in both the binary search tree and the heap, we're talking about a hierarchy of data. We're not necessarily talking about explicitly a tree. You can have hierarchical data that isn't actually a tree. In fact, when we looked at the vector-based implementation of a heap, that's a hierarchical container, even though it's not in a tree form. It's still in an associative container form, or not associative, a sequential container form. Okay, so today we're going to start talking about associative containers. And the big thing about associative containers is that we don't really care about anything other than that the elements inside the container simply exist, that they are there. Right? When I talk about the context, there is no reference of locality. Its neighbor doesn't have anything to do with being its neighbor, in the sense that a linked list's neighbor is directly related to its being connected to a node, right? When we talk about the front node of your linked list, that is the front node for a reason, which is why a stack and a queue can work, because we know that it is the thing that is either most recently put in or the thing that is most distantly put in, right? But in this context, for our associative container, the elements are not held in any context other than the fact that they simply exist. Now, this means that there is no implied order. There is no definition of, oh, this happens first and then this happens. The only thing here is that our container holds objects. And it turns out that the retrieval is largely based on key values. And we're going to talk a lot more about how this retrieval works next week on Wednesday. right? There's no implied order. That's the big thing here. Now, when we look at the standard template library, we're going to shift back into actually having an STL to look at. The STL outlines the associative container objects. We have set, we have multi-set, map, and multi-map. And today what we're going to be talking about is specifically set and multi-set. That's going to be where we're going to focus. On Friday, we'll talk a little bit about maps and multi-maps. Okay, the whole point, again, remember, is that we don't care about the location of our elements. All we care about is that those elements do in fact exist in our set. All right, let's get into it. Sets. So let's start by talking at a high level about what a set is. So for those of you that have taken discrete or have done a little bit of set theory type stuff, it's all going to apply, right? The name set comes from those areas. So when we talk about a set, we're talking about a collection of items. Now, we have to ask a question. This first one, we have a set of 1, 2, 3, and 4. We then have a set of 4, 3, 2, and 1. And then we have a set of 4, 2, 3, 3, 1, 1. Now, this first set is a set, right? That's good. Not a problem. That is in fact the definition of a set. And actually, the second one is also a set. Now, this is where math and CS decide to diverge for, I don't want to say complicated reasons. They're actually really simple reasons. It turns out that in CS, it doesn't matter, but in math, it matters a lot. So technically, this last set in discrete is not a set. Sets have to be, 1-to-1? In this case, we can have duplicates in our sets. That's what a multi-set is, and that's okay. So when we talk about a set, all we're talking about is a collection of items. So this gets into what can we say about all three of these? Well, they don't all have the same number of elements. That's different, right? The bottom one has 6 elements and the other one have 4 elements. But we can say that they all contain the same data. They're all equivalent to each other from the perspective of being a set. They all contain 1, they all contain 2, they all contain 3, and they all contain 4. Even though the internal structure may be different, what we can say is that they're all equivalent to each other in terms of the set that they are representing. Because again, sets don't have anything to do with order. They don't have anything to do with duplicates per se. They have more to do with, is a thing in this or is a thing not in this, right? It's basically just this binary of yes or no. So in this case, we can say, yes, they're all the same set. All right, so this leads us into an interesting space of like, well, Scott, why do we care about this? This seems like really sloppy arrays. We should figure out how we can do this better. So let's think about some operations that we can do with our set. So let's suppose that we have 2 sets. One set has Rey, Finn, R2-D2, and Chewbacca, and then the other set has Luke, Chewbacca, Darth Vader, and R2-D2. Now, we can see that these are different sets, but they also share some elements, right? And we're talking about Chewbacca and R2-D2, right? Chewbacca, the element shows up in both sets. So does R2-D2, showing up in both sets. So let's look at what that does. So first thing we can do is a union. This is going to add the 2 sets together. That would give us a set, if we're talking about a single set, a non-multi-set, that's going to give us a set of Rey, Finn, R2-D2, Chewbacca, Luke, and Darth Vader, right? R2-D2 and Chewbacca don't get added because they've already been added. If we have a union, that means we can also come up with an intersection. This is where they overlap, and that would be R2-D2 and Chewbacca, right? The 2 things that are similar between the 2 sets. We can do differences. The difference of A minus B is going to be basically the elements of A and then take out the elements that would be in the intersection. So that would be R2-D2 and Chewbacca would get removed. That just gives us Rey and Finn. And then we can also do the other difference, right? The minus sign implies that the order matters a lot, and in this case it does. For here, we're going to take B, and we are going to take out Chewbacca, and we're going to take out R2-D2, right? In that case, we'll be left with just Luke and Darth Vader. Okay, so that's a little bit of a kind of motivation here. We could easily come up with this idea that we could generate a set of usernames and then compare 2 usernames to see if they're in 2 different databases. We could certainly come up with a set of locations if we're doing like a map application, and we could specify the ones that are unique to map A versus map B. There are ways that we can do all of this in kind of janky ways using a vector or a list, but it turns out that when we use a set, this identification of what is and what is not in a set turns out to be very fast. And the reason it's fast will come into next week on Wednesday when we talk about hash tables. But it turns out that these operations of A plus B and A star B, you might think at the very first level that, okay, well, the union is going to be identify all of the things that are the same. That's going to be essentially an n squared operation if you're doing it in a vector form, right? We have to iterate through every single element in my A and then compare it to every single element in my B. That means that I'm going to check n times for Ray, I'm going to check n times for Finn, I'm going to check n times for R2D2, and n times for Chewbacca. That is an n squared operation. It turns out that we can get much better efficiencies based on how we're going to actually implement these. So again, bear with me for a sec. It turns out that the STL, as we've already outlined, has a set container. We're going to do include set, and then we have the ability to use this set very similar to how you would use one of the other containers. It turns out that for the STL, binary trees are often used in the implementation of sets because binary trees are going to allow us to have quick access into what is contained inside. But again, we don't necessarily have the requirement that anything is in particular order. Now, I just said nothing is in particular order, but it turns out that we kind of do have an order. We're going to have iterators, and the reason we have to have iterators is for the same reason we had to have iterators for lists, which is that we need to have some way of being able to point to a node inside of a set. We can't necessarily say something like set subscript 1 to get the second element of a set, but we still might want to be able to point at the general location that we just looked for. So this leads to the question of, okay, well, if we're going to have an iterator, then iterators can be decremented and incremented. So what are those orders going to be then for the iterator? Well, it turns out that a set actually does keep things ordered, but that's not a requirement. The iterators are going to give back the smallest to the largest objects, but this isn't necessarily a feature. It's more of just a element of how it works, right? So don't lean into this idea that a set is going to give you back ordered iterators. The point is just like that's actually how they work, but the way we use them is more for kind of keeping track and keeping place with where we are inside of a set. All right, we have another method called count. This is going to allow us to count the number of duplicates of an item. So thinking back to that original set, if we had 2 4s in our set, we could count on the value 4, and it would return back the number of times that occurs in the set. Now, this leads to an interesting question. Does a set have any duplicates? We haven't really talked about multi-sets, but the answer is no, right? A normal set won't allow duplicates. However, multi-sets do. For this conversation, I'm going to keep talking about sets as the singular set, not as the multi-set. I have a slide at the end that kind of talks about the big overview between the two, which again leads to this weird question of, wait, Scott, did you just say that a single set has a count method that can only ever return 1? The answer is yes. It's a little weird. Again, the reason here is the same reason that we have an iterator for a vector. It's there to provide a common interface. Both set and multi-set have a count method that is the exact same. So because they both have the same count method that is the same, we're going to have our single set either give us a 1 or a 0. If it has the element, it'll return back 1. It has a count of 1. And if it does not have the element, it'll return back a count of 0. It does not have the element, right? I know it's a little weird. I know it's a little strange. At this point, I think you've got it, though. Some other methods. We have an empty method that will tell us if our set is empty or not. It's always useful. We've got an erase. That's going to allow us to go into our set and remove an item from inside the set. We're going to be able to delete everything from inside of our set. This just allows us to clear everything out, get back to a steady state. We have access to a find method. Now, find is a little interesting. We're going to pass in a constant reference to an item, and then that's going to pass back an iterator to that item, right? The reason we're doing this is so that if we want to manipulate that item, we can via the iterator. This would be similar to like passing back a pointer, but we don't want to do pointers because that math will get messy. So instead, we're going to use iterators as kind of smart pointers. Okay, let's keep going. It turns out insert is weird. Insert's going to be weird, again, for multi-set reasons, not for single set reasons. So the very first kind of behavior, the overload of insert, is going to take in an item, but it will return back a pair. Now, we haven't talked about pairs yet. It turns out pair is a struct that is part of the standard template library. Pair is just simply a thing that holds two types. That's it. There's nothing more complicated than pair. It's just item left, item right. That's it. And so insert is going to return back two things. It's going to return back the iterator of the location of the item if it exists, and then the second element is going to be true or false if it was added or not. Oh, I shouldn't say if it exists or not. It will exist because insert will always add the thing. This bool is going to be basically, did it already exist or did we just add nothing, right? In both cases, our iterator will still point to the item that is in the list. Again, I'm going to say that again really quick. So we're inserting. I thought we were finding for a sec. We're inserting. So we're going to insert an item. The thing that we get back is the iterator that points to that item and the Boolean that tells us, were we successful in inserting that item that we wanted to? The case in which it would be no, we can't insert that item is going to be if it already exists. All right, in a similar way, we have the ability to pass in an iterator, both a first and a last iterator, and then the insert method will insert all of those items from first to last. What's important here is that this iterator does not need to be a set iterator. You could pass in a vector iterator, or pass in two vector iterators. That's fine, right? It's going to basically call first plus plus and then insert whatever first plus plus is dereferenced to, right? We're going to always be pushing things in. As a heads up, this is inclusive of the first item. That will be included, but it's exclusive of the last item. The last thing is not inserted. Okay. So let's keep going. A couple things just to point out, things that you need to be aware of. Remember that things are going to be stored in order, but again, that's only because of the underlying implementation. That's not a requirement of set. So don't necessarily lean into that when you're using them in application. Right? There is no subscripting operator. There is no array-like address operator. Everything is going to be accessed via an iterator or via the find. And that there's no duplicates, again, because we are in the regular set. We're not in multi-set. Okay, so let's look at multi-set for a sec. The only differences here are that we allow for duplicates. And when we go to do an insert, we will always add the item. Even if it already exists, we'll still add it. When we do an erase, this is important, erase will remove all occurrences of that item. It's not going to remove just one instance. It will remove all of the instances. And then similarly, count is going to operate a little bit differently, which is why we have a count for a single set. Our multi-set also has a count, and that's going to return back the number of items that match the thing that you are trying to count. All right, cool. So for Friday, you've got basically one homework question that's just asking you what each line of code is going to do using a set. I would highly suggest you just copy and paste that into a chunk of code and run it, see how it works, play around with it, fiddle with it, get a good intuition of what that set is doing. Now, you might be asking yourself, oh, Scott, this is a short lecture. Yeah, you're right. But remember, I also gave you that priority queue lecture on, Friday? So the whole point of this is that I'm going to be a little easy on you. On Friday, we're going to talk about maps, which is going to be the last, I think it's the last. Yeah, it's going to be the last STL container we actually talk about. And that's going to give us an intro into next week when we talk about hash tables. Now, next Monday is going to be the third exam. Please bring your questions or email me your questions or Discord message me your questions before class on Friday so we have some time to talk about any questions you may have. I'm probably going to post the exam on Friday and then have it be due next Tuesday. So I'm going to give you some time to work on it again. All right. That is sets and multi-sets. If you've got questions, bring them to our class session. All right. We'll talk later. Bye.